Hello and welcome to the Brain and Transcranial Photobiomodulation Virtual Summit. I'm your host, Dr. Joe Doduro. Today our speaker is Professor John Mitrofanis. He's a professor of anatomy at the University of Sydney, Australia, and he's been working in this field for over 30 years. He was awarded the Michael J. Fox Foundation with funding to look at the neuroprotective capacity of light therapy for the brain. Thank you, Professor John, for being here.
My pleasure. Thank you so much for the invite.
Awesome.
Why do the mitochondria become dysfunctional? Well, we don't know, but there's evidence for an environmental toxin. In a small number of cases, defective genes have been identified, and most of those genes are related to mitochondrial dysfunction. But the latest rage is that Parkinson's disease, just like Alzheimer's disease, is a prion disease, that you get these abnormal misfoldings of various enzymes, which is fine if it's just one or two cells. But the problem is this abnormal misfolding starts to spread across the brain like the coronavirus from China across the brain. And that causes the dysfunction of many neurons. And the most mischievous enzyme spreading across the brain than you might have heard of is alpha in Parkinson's disease is alpha-synuclein. Current treatments for Parkinson's disease, dopamine replacement drug therapy, which aims to replace the lost dopamine from the system, and that's usually followed by deep brain stimulation, which the principle behind that is to try and correct some of this abnormal activity of the nuclei, particularly the subthalamic nuclei. Now, as a general rule, these treatments treat the signs very well, particularly initially, particularly in the case of dopamine replacement drug therapy, but they both suffer in that they don't stop the pathology. They're not good at stopping the disease progression. So as we speak, there is no effective disease-modifying or neuroprotective treatment available for Parkinson's disease patients. So as you may appreciate, there's a real need to develop one. And some of the more recent ones have been targeting the mitochondria. Let's help the mitochondria function better and avoid the distress. And that's where photobiomodulation comes in. And if you indulge me, from here on in, I'll just call it light therapy. And a lot of people, mainly by these wonderful reviews here, have shown that light within these particular wavelengths, or thereabouts, have a big influence on cell function and survival. That photons can stimulate a chemical change in cells, that light energy can be converted to metabolic energy with a subsequent influence on cell function and survival. So how does this work? Well, here we have a neuron here. Let's assume that the light hits the neuron flush. The target is the mitochondria. That seems to be the main target, and it's absorbed by a photoacceptor. The most popular one to date is cytochrome oxidase C, but Mike Hambler's work in particular indicates that there may well be others, and the real target seems to be water within the mitochondria. The interfacial water absorbs the light. The bottom line is that after it's absorbed by the mitochondria, there's an increase in energy. There's an increase in fuel for the cell to function, ATP energy. And that leads on to a lot of other good things. It increases transcription factors in the nucleus. I think around about 20, 25 have been identified so far. And that leads to an expression of good genes, protective genes, stimulatory genes that really help the cell function better and avoid distress. And that was one of the great things that I loved about light, was that it helps the cell use things that it has inbuilt within already, stimulates inbuilt things to help it survive any insult and to function better. So our rationale going back some, 12 years now, is that if if mitochondrial dysfunction is so central to the pathogenesis of Parkinson's disease, and if light helps stimulate mitochondrial function, why don't we put the two and two together and see if one helps the other one? And this is how I got involved in this work. It was this man here, Jonathan Stone. We were having a cup of coffee, as most science usually happens from either a cup of coffee or alcohol. But in this case, it was coffee. And he was telling me that he's come across this method from Janice Ells that helps stimulate mitochondrial function. And almost at the same time, I was telling him that Parkinson's disease is mainly a disease of mitochondrial dysfunction. We thought, why don't we get our fishing rods out and our fishing tackles and go fishing? And I know funding bodies don't like the idea of anybody going on fishing expeditions, but goodness me, there's lots of fish in the lake and the sea, and we know we're going to catch something. So that's what we did. We went ahead and tried a few things to see if one helped the other. Now I've got this image here just to remind me to talk about the concept that this method is not necessarily new. There's evidence that the ancients had some idea of the healing properties of coloured light. Now for the less imaginative among you, this looks like a couple of Egyptians holding some giant vases, maybe some snakes in there. But for the more imaginative among you, this looks like a couple of Egyptians holding some giant light bulbs. And here's the cable leading to a battery source. And I've spoken to a couple of Egyptologists at Macquarie University here in Sydney, and they said to me, John, you know, it's not so outrageous. They did have some idea of how the battery worked, so it's not too far out of the realm. But I think it's one of those stories you need a little bit of seasoning, or a lot of seasoning to believe. Like I said, it's a good story. So we went ahead and looked at animal models. And at this point, I'll just say, look, there's no perfect model for Parkinson's disease as there is for most diseases out there. So the more data you glean from a number of animal models, then the better the picture you get from the situation in humans. We use rodents as our primary animal model. We use toxin-induced models, MPTP and 6-hydroxydopamine, 6-OHDA model, and they are toxins that cause a degeneration, rather specifically, of the dopaminergic cells in the substantia nigra. We also had access to a couple of transgenic models. We and a group in Switzerland have used a transgenic model which were genetically engineered to cause a degeneration of the dopaminergic cells in the substantia nigra. But we also had the rare opportunity of using the gold standard of animal models, the monkey model, the non-human primate model. And for that, we used the toxin-induced model, the MPTP model, which, like I said earlier, causes a degeneration of the dopaminergic cells in the substantia nigra. Now, for today, I'll talk about changes in behavior, where the light changed the behavior of these animals, improved their locomotion in particular. And the Holy Grail here, was it neuroprotective? Is it saving cells, neurons that would normally die as part of the toxic insult? So, so here we go, going back to my analogy here with our Volkswagens. Here's our fire, the mitochondria. Is the light application here actually acting as a fire extinguisher? Is it putting out the fire in the Volkswagen? And not only is it putting out the fire, but is it getting the Volkswagen back to working order? Is it getting back to working order and functional again? Because a good, well-functioning Volkswagen is a pleasure of life. Now, just before I go on a little bit, I just want to talk about ways in which we applied the light and issues of penetration. Now, in the rodent, we applied the light extracranially because we've got no problem with penetration. Where the substantia nigra here is only around about 5 millimeters from the light source, so there's no problem with light reaching the target, hitting the cells directly. And here is a little fellow getting some light treatment We mainly used 670 red light. We used other wavelengths, but 670 is the main one we used, and that's the main one I'll talk about today. And that's a little fellow getting some light application, and they really liked it. And we know that because once the light went off, they kind of looked up at us and they said, "Can we have some more, please?" Very much wanting some more. And this is the work of some wonderful students of mine. Victoria Shaw, which really started her PhD looking at this issue in the rodent. That was followed by Cassandra Peoples. Daniel Johnson was a postdoc that joined at that time, and I think he's giving a talk too at some point in the proceedings. And Nabil El-Masri finished off the work a few years ago, and that was the rodent, like I said. Now, in monkeys, we've got a bit of a problem. Monkeys, we've got a thick cranium and thick meninges, which is the connective tissue covering of the brain, and we've got some 40 or 50 millimeters of brain tissue before we get to the area of distress and the substantia nigra in the brainstem. So applying the light extracranially, and we and others have measured the penetration of light through body tissues, and we're talking 20 millimeters, maybe a little bit more, but really not much more. Certainly not 40 or 50 millimeters. So applying the light extracranially, it's probably not going to get to the area of distress. So for this species, we developed an intracranial device where we put an optical fiber in the midbrain so we can shine the light directly on the area of distress. And really this was the work that I did with this man, Alim Louis Ben-Abid. And many of you may know him. He is the father of deep brain stimulation, which is the current surgical treatment for Parkinson's disease. And when I told Ben-Abid about the neuroprotective properties of light, he said to me, "John, we have to develop a device for humans. We have to develop an intracranial device to get that light close to the substantia nigra." And that was what we did. And we started around about 2011. These are the wonderful people that worked on a project in Grenoble. Cecile Moreau, which she's Ben-Abid's lieutenant in the group, a research fellow. Napoleon Torres, another research fellow in the group. Florian Reinhardt was a PhD student that, like all good PhD students, did a lot of legwork in the study. And Claude Chabrol was the wonderful engineer that made the device. And here is the device here, just before it was implanted into the monkey brain.
Well,
and you can see the little spot.
There it is. Very
you can see the little bit of red light coming at the tip, and we just tested. Yeah, we used to test it just before we put it in. Now, for this experimental study, we wanted to give the neurons in distress the best chance of survival. And to give those neurons the best chance of survival, we wanted to make sure that the light hit the cells directly. Mm-hmm. So using it extracranially in the mouse and intracranially on the monkey, we were confident that the light hit the cells directly. Now, today I'll talk mainly about the monkey results because our earlier stuff on the rodent pretty much reflected what we saw in the monkey. So I'll talk mainly about the monkey with a little bit of rodent stuff, but mainly about the monkey. So let's talk about our behavior, whether there were any changes in behavior. And we did an open field test, which basically we had a camera in front of the cage, the monkey cage, and that camera was linked to a computer program, and the computer did a trace over a 20-minute period of where that monkey moved. So here is the top of the cage, here is the bottom of the cage, and you can see that the control monkey over 20 minutes, he was moving around a lot, up and down the cage, up and down the cage. So lots of movement. Now look at the Parkinsonian MPTP treated monkey. He didn't move at all. And they don't call this the gold standard of animal models for nothing. That they do develop quite human-like signs of the disease. And he was really akinetic, very, very stiff. So he didn't move at all. But look at the light-treated animal. He was moving around the cage, certainly a lot more than the Parkinsonian monkey, not quite as much as the control, but certainly more than the Parkinsonian monkey. And really, I shouldn't say this, but I will. Up until that stage, I had been involved in hundreds, if not thousands, of rodents, and most of them got better. But as a scientist, you always look at it and you think, really? Is light actually stopping these cells dying and helping them survive? Really? So you always had that niggling bit of doubt. Well, I always had that niggling bit of doubt in my mind. And all those doubts were quashed when I saw this guy.
You became a believer.
I saw this guy.
You became a believer.
Yeah, well, I know. I mean, we did some 10, 15 monkeys, MPTP treated monkeys, and this guy was the first, and they're all akinetic, stiff as boards in the cage. First guy we did light treated, and he was moving around that cage like there was no tomorrow, and I thought to myself, goodness me. And I was actually in the lab with Ben Abid when we saw this guy, and we hugged. We hugged in the lab and we said, goodness me, we're right. We're right. And because he was the first one, we called this monkey hero, because he was our hero. Now, like I said earlier, they don't call this the gold standard of animal models for nothing. They do develop very prominent clinical signs of the disease, so we were able to assess them clinically. So we measured a range of parameters, whether, for instance, how active the animal was, whether the animal had tremor, how stiff the animal was, and we added them all up and gave them a mean clinical score. So the higher the score, then that meant the more impaired the animal was. Very similar to what the scoring system in humans. And you can see here that the control animal had a clinical score of nothing, 0. I mean, that stands to reason. He wasn't impaired at all. So he wasn't impaired at all. But look at the Parkinsonian monkeys, the MPTP treated monkeys, much higher clinical scores. They have scores of 23, 24. Light treated animals, much lower impairment, much lower mean clinical scores. And we did 11 of these monkeys. And I should just say that a couple of these monkeys didn't get sick at all. They had clinical scores of 1, 2.
Okay.
So it was quite a big drop off in mean clinical scores. Now, I'll just talk a little bit. I'll just show you some videos here in the rodent, and this pretty much reflects what we saw in the monkeys. And you can see here are the control mice, and you can see they're moving around the cage pretty quickly and pretty easily. This is the MPTP treated monkeys. Oops, sorry. You can see that they're quite akinetic. They're not moving hardly at all. But look at the light treated animals here. They are moving a lot more than the Parkinsonian animals here. Not quite as much as the controls, but certainly much more than the Parkinsonian MPTP treated mice. Very similar to what we saw in the monkey. So overall, it improves behavior, locomotive behavior, and reduces the clinical signs of in these animal models. Well, what about the Holy Grail? The golden ark of the covenant. Is it neuroprotective? Is it stopping cells from dying, cells that would normally die as part of the toxic insult? For that, we counted the number of cells in the substantia nigra, the dopaminergic cells, and we used an antibody to tyrosine hydroxylase. And tyrosine hydroxylase essentially makes dopamine, so anything that's tyrosine hydroxylase positive in this region would be dopaminergic, and here's some pretty good looking dopaminergic cells in the substantia nigra. And here's our results. You can see that the Parkinsonian MPTP-treated monkeys had fewer cells than the control. That's good. That shows our regime was effective. Look at that. Always more cells in the light-treated animals compared to the Parkinsonian animals. Not quite as much as the controls, but certainly much more than the Parkinsonian animals. If we look at the real images, here is the control, here's the Parkinsonian Nigra, and you can see the light-treated Nigra had more cells than that. And as a humble anatomist as I am, that's what I want to see. I want to look down the microscope and see a difference. And I've always impressed that on my students. If you want to tell me there's a difference, show me down the microscope, show me the difference. I'm much more likely to believe that than some magical statistical test that's reached magical 0.0507 value. Having said that,
and as a neuroanatomist, you would look at the neurons. This is the Holy Grail. You did it.
Absolutely, absolutely. So it's my protective. It's protective in the animal models. But that's great. It works in animal models. But will this work in humans? And as a scientist, I say, well, how will this work? How will this work in humans? Humans, because we've got a bit of a problem. The problem is that the intracranial method in human hasn't been developed yet. Clinical trials have been approved in Grenoble, and they'll probably start within a year. But for the patients of today, there is no intracranial method available for them. We have to use the extracranial method. And if we had a problem in the monkey, we've got a bigger problem in the human. We've got, well, some of us have hair, not all of us, but some of us have hair. We've got thicker bone, we've got thicker meninges, and in the monkey we had 40 or 50 millimeters of brain tissue. We've got double that in human. We've got 80 to 100 millimeters of brain tissue. So if it wasn't going to get there in the monkey, it's not going to get there in the human. So how will this work in human, or will this work in human? Well, we think it might work in two ways. First up, it might work indirectly using something in the circulation. And it could be neuroprotective using this method. So if we apply the light here, there's plenty of blood vessels, plenty of lymphatics in the skin of the scalp and within the bone here. It could activate something in the circulation, or something in the immune system or stem cell system, and this might act as a middleman. And that might use the circulation to get to the area of distress in the substantia nigra pars compacta and help those cells survive. And we've got actually evidence in animal models of the disease that if you shine the light on the animal's leg or the back, it will actually help cells survive in the brain. So there must be something going on in the circulation. And the results are using this indirect method. They're not quite as effective as the direct stimulation, as if the light was hitting the cells flush, but indirectly it's almost as good as the direct, but not quite as good. And this is, you might have heard of this effect. This is the so-called abscopal effect, using the circulation to, or applying a method to a distant organ and getting an effect in an organ far, far away.
Well, Professor.
So it could be.
Professor.
Yep.
Well,
yep.
I had lunch with one of my colleagues from 30 years ago when I graduated, and they said, he goes to the bartender, he goes, you know, this guy used to, first month of school, he'd raise his hand and say, Professor, that's not correct. Okay, so I'm not going to be that bold, but I have a question about this. Since the extracranial, right, the transcranial aspect is something that I'm sort of pay attention to. So if I was to ask you the indirect stimulation using the immune system or stem cells that could be activated by whatever tissue is touched, right? They would have to have those, if we're talking about the brain area, some of those tissues would have to be involved, correct?
Sure, yeah.
And,
Yeah.
and then when we talk about the circulatory system, if we have the subdural, just the scalp and the blood vessels that go across your head and everything like that, those were going to be, that blood doesn't actually go intracranial either. Am I correct? It's going to be venous circulation or superficial. It's not going to go from the head blood vessel deep into the brain. Am I correct?
Probably not immediately, although there have been, just as an aside, there's been a recent study showing that there's little channels through the brain here that actually find their way into the dura.
Correct.
I mean, eventually it would get there.
But what I'm saying, the circulation to the deep structures are deep anyway. They start here and go this way. They don't go from the outside of the head in that way. So it's kind of I just wanted to be a little bit clear in our understanding that it's you can get the light to some tissue that are going to have some effect. And again, in Latin, abscopal means off target. So
there you go.
You aim for the target is here, but you're going to shoot there, and it finds its own way like a self-directed missile.
That's exactly it. That's exactly it. And Ann Liebert and Daniel Johnson will probably talk at some point about abscopal and applying the light to the abdomen and getting an effect. It's the same thing. You're stimulating something in the circulation, and it's eventually getting to an area of distress.
All right, that's fine.
The latest rage, and I should just add this, the latest rage in all this is that people have discovered free mitochondria in blood plasma. So there's mitochondria floating around in the blood. Now, whether the light is stimulating them directly and then getting an effect on a distressed cell, and there's another lovely study showing that microglia actually pick up these mitochondria and feed the distressed neuron with good mitochondria. And that's all fitting into this abscopal effect, that it's happening, something else is happening in the circulation and it's helping these distressed. So that method, it could be neuroprotective.
Correct. And you also mentioned a couple things that I wanted you to repeat in this little section here, was that the indirect effect is that some of the studies have shown we can put it on the belly, on the leg, the tibia, right? And other flat bones, small bones that can push out more stem cells, if you will. Correct? Is this what
Yeah.
So these are it's still the brain, but we're treating other areas and other areas.
That's right. Yeah.
Wanted to bring.
But the great thing, the good thing about the additional benefit, I think, of applying to transcranially rather than anywhere else, although the abdomen seems to be a hot spot, is that you could have symptomatic effects. So even from this extracranial application, even though the light won't reach the area of distress here, it can still reach the superficial areas of the brain. It can still reach the cortex. So it might stimulate something in the cortex, which then these descending pathways to the striatum or the basal ganglia or brainstem or even down the spinal cord might stimulate these healthy neurons, and then the patients start feeling better or they start moving a little better. That's not neuroprotective, that's just more symptomatic.
Very good. Very good.
And what we and others have shown that it can actually stimulate healthy neurons. And this is something I've been involved in along those lines more recently with Luke Henderson, who's a professor in our university, and he's a guru with All Matters MRI, and Khala El Khoury, who's doing a PhD with me, and we with them we looked at whether the idea, and I've always been fascinated with this idea, does transcranial or extracranial light actually change brain activity? Can it change the activity of a healthy neuron? So like I said, that's getting back to this thing here. Does it change the activity of this? So with this study, we had some young subjects, healthy subjects. So we've got about 20 of them. They're all Khala's friends, but they were healthy and young. And what we got them to do is we got them to finger tap while they were getting scanned. So it's just a simple task for them to do this. So what we did is we scanned them. They came out. They had either light treatment or sham. Then they went back in and they were scanned again. And these images here show the differences between a pre-light or sham as against post. So with the sham treatment, you could see that pre and post, there was no difference, as you'd expect. They had sham treatment, there was no differences in their brain activity. But look here, with light treatment, there were changes in brain activity. That the light actually changed the activity of a number of brain areas. Now, Luke, like I said, he's a guru with MRI, and he said to me, okay, this area is particularly interesting, this parietal association cortex. And as soon as that lit up, I thought, goodness me, that's attention. That's focusing attention on this. And he said, okay, let's take a little spot out of there. And like I said, he's a guru with this, and he knew what he was doing. And he said, we'll take a seed. So we'll take a spot out of parietal association cortex, and he called that the seed here. And what the next thing does, from that seed, you can look at any changes in functional activity with that seed that light creates. And these, you can see that these areas of the brain actually change their activity, functional connectivity with this area here. And these little blotches down here particularly interest me because they were part of the so-called default mode network. The activity, this is the network that's pretty much large-scale network that's happening when we are not actively doing anything. We're in a default mode. We're actually daydreaming or not thinking about anything in particular. And Mani Naser has, are you familiar with Mani? Mm-hmm. Mani Naser has come up with the hypothesis that light actually influences or corrects the balance of the default mode network. That in cases where the default mode network may be dysfunctional, it corrects the balance. And in this case, where we were doing the finger tapping, we put it to the we predicted, or we thought that those areas have become active. Have basically, what light does is that it deactivates the default mode network, so we can focus attention on the finger tapping, and it's able to do that much easier with light after light treatment than without. But that's another story. What I wanted to just take home from this was that light can certainly change the activity of the brain.
Okay, now, if I may, just because there's a lot of information here, my question is, one, they did right-handed, did they do hand-dominant tapping? Not just one-handed, were they all right-handed people?
I would assume so.
Right.
I don't know. I can't remember offhand whether they're right hand, but certainly the right hand.
And then where did you treat them transcranially? What did you just put? What was it? Laser? Was it light? What was it?
It was the V light.
The V light.
V light from Lulin. Yeah.
Very good. Very
so
good.
we had them on. Yeah. So when they came off, they either had. And the great thing about the V light was that it was 8-10 nanometers, so they didn't know whether it was on or not. And Khala had put, for the sham, had put tape around the battery box, so they didn't know whether the light was on or not.
Perfect.
But the main point I wanted to just to raise here is that, yes, it can change brain activity. So it's doing something to a normal, healthy neuron. So it could have an influence here, a symptomatic effect on brain activity. Whereas, this indirect system, there could be a neuroprotective angle as well, using something in the circulation. So with that, this is where the applications to human came in, where the development of some helmets was put into place. And really it's the work of this lady here, Catherine Hamilton, in Tasmania, small little state I told you about at the start. And she was helped by her wonderful husband, David, who was very much an engineer on the project. This guy here, Frank Nicolason, was the terrific geriatrician that was so open-minded and so encouraging of his patients to use Catherine's helmets. Max Burr is a local politician, and like all good politicians, he had the gift of the gab, and he was telling everybody he could possibly within earshot that of the benefits of using Catherine's helmet. And Barbara, as Max's lovely wife, this is my wife here, who had nothing to do with the project, but she came along because we had a wonderful lunch that day, and she had some nice glasses of wine, and she got quite drunk. In fact, she looks quite intoxicated there, and she's happy. It's always good to have happy wives. Anyway, so Catherine first started making buckets, light helmets out of buckets, sometimes out of lampshades, and they were lined with two types of light, either 670 red or something in the near infrared range, 940 or something in the 800s. And normally the patient would put the 670 first, and that would be followed by the infrared. And in most cases, 20 or 30 minutes, one wavelength after the other, twice a day. So these are some patients using the early buckets. They're not aesthetically pleasing, but goodness me, they were effective. And then later, Catherine developed these coronets, which she has for sale for patients. And so these are the coronets, but the same principle, using red light followed by an infrared afterwards. We had one chap here who was quite the novice electrical man, and he developed an intranasal thing. And let me tell you, that was as you could probably get the scale of it, it was pretty long. And he stuck that right up his nose, and his thinking was he was trying to get it as close to the sphenoid bone as possible, close to the brainstem as possible, to shine the light in there.
It looks like he got it there.
No, he got it there, and he actually offered it to me to stick it up my nose, and I said, no, please, it's fine. And he was a retired surgeon, and he entered the game with much skepticism, but I'll show you his results in a moment, but that's what he used. So here is our findings here from 8 movement disorder patients. One had progressive supranuclear palsy, which was a chronic degeneration of the brainstem and the basal ganglia. And it's often misdiagnosed for Parkinson's disease because the patients often have very similar signs to Parkinson's patient. So this was FH here, and the other 7 were all confirmed Parkinson's disease patients. They're all the signs, major signs and symptoms for each patient. Who was ML? ML was the chap who had the intranasal thing. The rest had either buckets or the coronets.
May I ask one question, Professor?
Sure.
They did not have dual. They switched the helmet. So they switched the helmet. They put the red on. Then they took that one off and they put the infrared on, or was it? No. The helmet had both. No, the helmet had both 670 and infrared. But they did them one at a time. They did them one at a time.
Yeah, and it would happen automatically.
Okay, so it went red and then it went infrared. 20 minutes. Okay.
Yeah.
Thank you.
All right, so they all started well after the diagnosis, obviously. Very few side effects. Some, I think one or two of them had some skin irritation, but that died down. Some of them had nightmares after they first started using, but then again, that died down. There was virtually no side effects to talk about. Now, I'm going to color code each of these signs or symptoms in a minute. If that sign or symptom comes up red, that sign or symptom was worse during light treatment. If it comes up yellow, there was no change. And if it comes up green, that sign or symptom was better during light treatment. So here we go. Plenty of green, a little bit of yellow, but only one red. From all these signs or symptoms, there was only one red. Well, this patient had a little bit of worsening tremor during the period. Couple of things I just want to make note of. Each of these observations were rather subjective. They were either by the patient themselves, their carer or the person they were living with, or their medical practitioner. In other words, Catherine Hamilton or Frank Nicolason, the geriatrician. Now, 4 issues I just want to touch on with these results or these findings. First up, most of these observations was not by the patient themselves. It was by others, the carers or the medical practitioners, which said to us something about the placebo effect, that other people were noting the differences and the person that was undertaking the treatment didn't notice much of a change. Obviously, there has to be a clinical trial, but that was an early indication that this is not necessarily a placebo effect that we're seeing. The other thing that works against the placebo is that each of these signs or symptoms got better after a while. It wasn't like overnight. Most of these signs or symptoms improved 1 to 2 months after daily application. So it took a while to get going. The other thing that we noted is that you had to continually apply the light. If you stopped doing the light, then the signs or symptoms tended to return. Catherine tells this wonderful story of BS here, who was using the light treatment and everything was working fine. And then things went completely haywire. He got the flu, not the coronavirus, but he got the regular flu. And once he got the flu, everything went berserk. And most of his signs or symptoms returned. So it was almost like the body was saying, hang on, no, I can't deal with your Parkinson's right now. I have to deal with the flu, this acute flu-like attack. And after the symptoms of the flu subsided and he continued to use light treatment, then the benefits started to come back. And that was, I think, an interesting observation from both Frank and Catherine. Third thing I want to just touch on, we're talking about a long-term study here. We're not talking about a couple of weeks. A lot of these patients were 2 years, and now Catherine's still monitoring them, and some of these patients are 3 years of treating them with the light. But here we've got 2 years. We've got PN here, MH. The others are up to a year to 6 months. So we're talking about long-term benefits, sustained benefits. And we're very confident that all these changes are not due to anything else. They are light-induced, and they're not due to a change in medication. In fact, some of these patients had a reduction in medication during their light treatment. Some of them had no change. This chap here had an increase in his medication because his tremor got a little bit worse. But look, these benefits were evident before the change in medication. So like I said, we're pretty confident that all these changes were not due to anything else and were light induced.
I think there's more people, from what I understand, more people are doing this though, aren't they now? Did they add more people? You're going to talk about that.
Well, I'll just get to my final and I'll talk about
the compliance thing. Is that, think about it, these people are taking, half an hour, maybe an hour a day regularly. They're committed to it. I know. It's a beautiful thing.
And that's the thing, Joe. Catherine tells me that they're unbelievably compliant. It's not like they forget to take their medication, or they don't do that, or don't do this. But with this, the compliance is remarkable. It's something that and the effects on their mood. I mean, the psychiatrists, you probably heard that psychiatrists are getting very interested in this because it's improving people's mood. People that are chronically depressed are feeling better. And a lot of these improvements go back to what I said at the start, the non-motor symptoms of the disease. Things like improvements in smell, improvements in confidence, fatigue. They have interest. Their apathy seems to improve. So the non-motor symptoms seem to be a great benefit. And Catherine has put together a paper recently focusing on this issue, that with this light treatment, the non-motor symptoms of the disease there are much more improvements with these symptoms than the motor signs.
Correct, because it's all one brain. And what I want to also point out, that in my case report, and the thing that I looked at, and we sort of, you kind of got it a little bit, was the reduction in caregiver stress or caregiver output. Because the caregiver maybe has to sit the patient down and the mommy down and put the thing on and everything like that, but there's still compliance. And as the functionality of the patient with the neurodegenerative disease improves, the stress and activity of the caregiver goes down. And so this is what you kind of captured, tangentially, I believe, in this. It's something to look at. I think that's one of the things they're going to look at going forward.
No, that's a very good point. That's a very good point. Because not only the compliance is good, the stress on the carers actually improves. And a lot of the carers have been telling Catherine and Frank that, it's so good to have my husband back. And the husband, the patient would go, I feel as though I've got my life back. And that's a big thing that's often overlooked in Parkinson's disease patients, but they feel as though they've got more energy, they've got more zest for life, they feel better. Just in conclusion, I hope that I've convinced you in animal models it improves locomotor behavior, holy grail, neuroprotection, looking at a range of models from rodents to monkeys, and these early findings in the human, these 8 studies have really led on to someone like Anne Liebert, who I think is going to talk to you at some point soon. I mean, she is really the driving force, an instigator of several clinical trials across Australia, looking at the effect of light on patients. And she has come up with, essentially, quite remarkably, the same sort of results as what Catherine and Frank has seen in the Tasmanian study, that they feel better, they're moving better, and the improvements are there to be had. And Anne Liebert, together with Roberta Chow, who I think is talking to you, they're going to be developing this even further to a large-scale clinical trial. And really that's what we need. If we want to get acceptance in the scientific community, in the medical, particularly with neurologists who, tend to be quite fixed in their boxes, if we going to get acceptance of this as a viable therapeutic option, we need a placebo-controlled study, and Anne Liebert is really leading the way with this. And like I said, I'm pretty sure you're going to be talking to her.
Yep.
So finally, here's all the wonderful people that I mentioned that were involved in the work, from Sydney to Grenoble to Launceston here. And I didn't talk about the work in London I'm doing with Glenn Jeffrey on flies, but I'll thank him anyway. And there's our wonderful sponsors. So that's it.
You did a great job. Now, so I think you kind of launched on what the science is going to talk about in the future, we have trials and we have controls and placebos and all that, yada, yada. But, I kind of say, if you get a signal, if you put your compass out and you get a signal, run to the signal. And I think that's what's happening. And, those people that get better from light therapy, they try it. If there's no downside, we haven't really seen a downside with the stuff that we're doing. People choose to make their own and start it. So there's no downside. So yes, science and somebody in a white jacket might need his trials, but Millie Brown is more than happy to try it.
Yeah.
Do her own trial and N of 1 and see if she could get, hey, you know what? I don't put my keys in the refrigerator anymore, So everyone's happy.
Well, I'll tell you a wonderful quote from Max Burr, this chap here, the politician who, you really couldn't shut him up about anything. But he's very, very Australian. We have a term here called ochre. If you're really ochre, that means you're real Australian, And he's very much like that. And he said to me, he said, John, I don't give a shit about.
I want to see your face when you say this. Go ahead.
Okay. Oh, you didn't see my face. Okay. Where are you?
I'm right here.
Do you see me?
Yes, sir.
Ah, there you are. He goes, John, I don't give a shit about what Michael Fox is doing. I want something now. I want something for me, And I said to him, Max, I can't argue with it, It's all very well for the future, but these people want something for them today.
Correct.
Today.
Correct. And how do you see what do you see? You've been looking at this microscopically and macroscopically for 30 years. So turn the compass around and tell me, what do you see happening in the next decade with this light therapy type of stuff in the brain? What's your vision?
My vision would be that our good friends in neurology will actually accept the fact that something's happening here, and this is not just voodoo, and that if they thought about, I love that study by Pollock, I think it was a few years ago, that talked about fundamental interactions. And he talked about fundamental interactions, and if you looked at the way that light relates to water, and that's how light can change the composition of water. Getting back to the mitochondria, changes the composition of water in the mitochondria and improves the function of the mitochondria. When you think of that at a distance, you think, yes, something could be happening here. And that light can actually have an influence on how a body cell functions, and in this case a neuron. And I would like to see in some years' time that neurologists would say, okay, take your regular medication, but use light as an adjunct treatment, because you'll feel better. You'll feel better and you'll get improvements. And you may well be stopping or slowing the progression of the disease. And you could also have an option with an intracranial method that if in particular people, maybe early diagnosed people, that they can have this intracranial device inserted to basically stop the disease in its tracks. And that's what I would like to see, that looking at things like light treatment, exercise, which is of enormous benefit. And, something like exercise, people could readily understand that it improves the musculoskeletal system, circulation, but exercises changes the configuration and the function of the brain. It helps cells, exactly, it makes them function better. If a cell's in distress, it will help those cells. And what light does and what exercise does, it releases the same growth factors, the same trophic factors to help cells survive and to function better. So I think 20 years down the track, I'd like to see light used either transcranially, extracranially, or intracranially and be available as a treatment option to help slow the progression of the disease. And that's what I'd like to see it. And but first things first, and leave it with her clinical trials. Let's get a good effect with controls.
Thank you, Professor John. Thank you so much.
It's been such a pleasure.